to determine linear or nonlinear differential equations. The 4 rules of the game that determine nonlinear differential equations. So our first rule is dependent variables and or its derivative can't be raised by powers / exponents, first degree only, not to be confused with the order of the derivative. And so the first thing we need to do is to understand what a dependent variable and what an independent variable is. And so in this case, I want to let y be my dependent variable. So I'll put dep, and then I'll make x my independent variable. Alright. So I hope you guys are following along. So I said let y equal my dependent variable and x equal my independent variable. You can make any of these your dependent and independent variable, right? I can make t my independent variable. I can make a my independent variable. It doesn't really matter. But in this video, I'm going to use y and x for the most part, and I'll tell you when I change it. And so, how are we going to determine which is dependent and independent if we're given something like this? dy d of x, which is our derivative, our notation, symbolically, right? And so this is how I remember it. The dependent is always on top. So make sure your dependent's always on top and your independent's always on the bottom. And for me, so this is more of a simpler way. For me, this is how I know it mnemonically. I say d divided by I. And what does that mean? That means dependent divided by independent. And so now we answer the first part of our statement. What is a dependent variable? So now n is derivative, because this is its derivative, right? So now we need to go to what the rest of the statement is saying. So now it says, or its derivative can't be raised by powers / exponents, first degree only. And so what does that mean? So let's say I'm given my derivative, and I'm going to write my derivative in terms of y, right? So I'm going to put in y prime. You cannot do powers or exponents. As following the statement says, I cannot do square this. I cannot have y double prime and do cube it and n for any n number, right? And so I'm going to erase some of this stuff. Hopefully you're still following along. It says I can't have my dependent variable, right? Because y is my dependent variable, and I can't square it. And I can't have my dependent variable y and do whatever n number on top. So whatever yn or y double prime n or y prime n, etc., or dy dxn, I can't do that. That's what makes it non-linear, so I can't do that. Alright, so that's how you determine our first rule. So now we understand our first rule. Now we need to understand our second rule. It says no products / multiplication of dependent variables and or its derivative occur of itself, similarly to rule number 1. And so just like rule number 1, where we can't have powers or exponents, what happens when we multiply our dependent variable by a dependent variable? It becomes an exponent, or the power of itself. And so we can only have first degree powers. And so we can only have this, right? We can't have that. We can't have y prime times y prime. We can't have y prime times y. These are all what we'll say nonlinear differential equations. Alright, so our next statement says So we already answered 2 statements. Our next statement says, whenever a dependent variable or its derivative is self-contained in a function, for example, transcendental functions. And so what does that mean? And by the way, dy for rule number 2, so just in case you guys are a little confused, dy times dy d of x, that is non-linear, right? Because that's the same as saying y prime times y prime. So if you want to write anything down, write all these rules. So whenever a dependent variable or its derivative is self-contained in a function, for example, transcendental functions. And so what does that mean? It means functions like this: ey, sine y, right? Any function that so let's say I had a normal function, right? Let's say I had I can't even think right now, but let's say I had something like this. Let's continue with the examples I'm showing you. These are transcendental functions, and that goes against rule number 3. So, and I'll show examples right now. I'm just showing you the idea of how to do this. So now we answered 3 of the rules. The last rule says coefficients may contain the independent variable, but not while also containing the dependent variable and/or its derivative. The coefficients and the infinite series of what a linear differential equation are as following. And so this is how our infinite series, right? Our infinite series of a linear differential equation. And so if it's not as following, right? And this is more of a general idea. If our equation doesn't look something similar to this, then it's non-linear. If it looks something similar to this, it's linear. And we'll work on some examples right now, so you won't get confused on that part. Alright, the last part right here says, the additive combinations are permitted to have multipliers / coefficients that depend on the independent variable. No restrictions are made on the nature of this independent variable's dependence, or independent variable dependence. So it's the same thing right here. So all that's saying is for our a sub 0, right, it could have something like this: 2 of x, or a sub 1, a sub naught, right? That's a sub naught. And some people say a sub 0. It's the same thing. Maybe you could have a constant 1. We could have a constant 2, right? And for all of a sub n and a sub naught, everything can be written out like this, right? With the independent variable, which is our x. But it can't contain something like this. I can't have 2x y prime times y z and all these extra stuff. We can't have that kind of stuff. We can't have y squared. Now it could be separate from it, right? If we take it separate from itself, then that could be true. And we'll see some examples right now of that. But the independent variable has to be clearly shown that it's not a part of our dependent variable, right? And I'll show you one example right here really fast, and so you understand the fourth one, why this one's kind of important, or really important. And so let's say that we're given this y prime plus 4y. So we're given this, which equals 4xy. And it's just having it like this, it'll be hard to determine if it's linear or non-linear. I mean, it looks kind of linear if you're familiar with working with these problems. But if you're not, then we have to do the algebra behind it. So I subtract 4xy to the other side, and now I'm going to get negative 4xy, right? I pull out a number. Which number? Actually, I'm going to pull out y. I pull out y, and that's going to give me, so go up here, I'm going to have y prime, and that's, I want you to pay attention that this looks very similar to our general idea of how our infinite series works for linear differential equations. And so we're going to have, let's see, 4 minus 4x and y. And so, like I said earlier, when we could have something like this, we could have, let me think, I had said we could have 2x of y, right? And our a sub 0 could be this, or a sub naught, my bad. It could be this, so that's be a sub naught. And I'll go back to the example right now, and this is y. So this is our a sub naught. And then our constant right here, which is going to be 1, it's going to be a sub 1. So separate all that. Let me erase some of this so you can see it. And we'll work with, and then we're going to do actual big examples. So then, if this doesn't settle in, you can rewatch the video again, and then you'll be like, okay, I understand what he's saying a little bit more than I did before. And so this says a sub 1, which is our constant, right? So a sub 1 equals 1, and a sub naught will equal 4 minus 4x. And so this satisfies our fourth rule or definition. The additive combinations are permitted to have multipliers / coefficients that depend on the independent variable, our independent variable, which is x. No restrictions are made on the nature of the independent variable dependence. And so you could clearly see why that means right here. So this is not to get confused with rule number 2 or 1, right? Because we can multiply the independent variable by the dependent variable. So we could have x times y. But y can't be a power, right? It can't be squared, because then that goes against rule number 1. Y prime can't be a power, because then that will go against rule number 1 again. Y prime times y will go against rule number 2. Y prime times y prime, that goes against rule number 2. Let's say we have this contained within this function, sine of x y prime. That will not be a linear function. And what else? Number 4, we could have, like I said, we could have 4 minus 4x of y, and that will satisfy the bottom half of this, but we can't have 4y, so we can't have something like this. Let me think. 4y and let's see. Well, you could have something like this, right? Then you could change it up like this, because the variables you could interchange them, which just means the same thing. But we can't have, let's say, 4xy squared. So it's really basic. The last one is more, this rule is more for the x, the dependent variable. So let's look at some equations. Alright, so here's our first example. And if you feel like anytime you want to pause the video to work out the problem yourself, please go ahead and do so. So this is our first problem. It's going to be the derivative of d2y dx2. So plus y cubed equals 0. And so the first thing I highly suggest is to always write out our mnemonics, which was d over I, or dependent over independent. And so that just tells us for our given derivative is which ones are dependent and which ones are independent variable. The second thing I would suggest is to rewrite it implicitly. So rewrite the function implicitly. That just means we would change this into y double prime plus y cubed, because why would we do that? Because this is now implicit. It's easier to tell what our problem's asking us. So rewrite implicitly. And our third rule is, when you're working with these problems, is to know our tips. The third tip is to know your rules, to know the four rules. And so if you don't remember the rules, I would rewrite them down. I would write them down and then continue watching this video, because it would help a lot to memorize those four rules. So let's see right here. Does this break rule number 1? And it does, right? Because rule number 1 says we can only have a power or an exponent or a degree of 1, right? And so this has a degree of 3. And so this breaks rule number 1. And so this will make this question non-linear. And to add one more thing for this question, it breaks rule number 2 too, right? Because rule number 1 and rule number 2 go hand in hand. And so with that being said, it breaks rule number 1 and rule number 2, so it's nonlinear. What's the first thing we need to do? We need to identify which ones are dependent and which ones are independent variable. In this case, our dependent variable is x and our independent variable is t. And so now, what's our second thing we should do? We should rewrite it implicitly. So it's just easier to tell which is what. And so, what do we write implicitly? We always rewrite the implicit thing to be dependent. So our derivative is always going to be implicit for r dependent. So it becomes x prime. And so what's the next step? We keep going, so let's see. We write all this. Our next step is to know the four rules. And the first rule is the power rule. And so, does it follow the power rule? Yes. Right, because these are what? Independent variable. So we're really just focusing on our dependent variable for the first three rules. And so, is it a multiple of itself? No. The rule number 3, is it self-contained? Does it have a what do you call it, transcendental function within it? No. So we have to look at rule number 4 now. And what does rule number 4 say? Rule number 4 is asking about the coefficient. And so this number is our coefficient. So this would be our a sub 1 times a sub 1t, for be precise. And that's times x prime. So this is our a sub 1t, which is going to be 2/3 x prime. It doesn't break the rule. So this is a linear differential equation. And so why doesn't it break the rule? Because if you remember that the coefficient for the independent variable has the free will to be whatever it wants to be exponentially. It could have 1 million in front of it if it wanted to, times by the power of 1 million if it wanted to. but of course it can't be contained within the derivative of the dependent variable or the independent variable. So in this case it's not. And so what's the first thing we need to do? We gotta identify what's dependent, which one's the independent variable. Our dependent variable is y, our independent variable is x. Now we write it implicitly, so this becomes y double prime minus y times y prime, and times like that, which equals, what's this? Cosine of x. So it should have been an x. And so there's a big problem here. It's that this breaks the first rule, or actually the second rule, which is y, the dependent variable can't be multiplied by itself, and it can't be multiplied by its derivative, so that's wrong. So here's our next problem. And so what's the first thing we need to do is identify which ones are dependent, which ones are independent variable. Y is our dependent, x is our independent variable. Now we need to rewrite it implicitly. And so let's see, this becomes y triple prime, and this becomes plus 5x y double prime. This becomes plus, let's see, y equals sine of x. And this equals 0, so y sine of x. So what would be our answer right here? Well, this is a of 2, which is okay, and it doesn't break the first 2 or 3 rules, so it's going to be linear, right? And this is okay, so that's our answer. This is okay because it's not the dependent variable. Alright, so here's our next example. It says y prime plus e of y equals x. So does it break rule number 1? No, right? Because there's no power. Does it break rule number 2? No, because there's nothing to multiply. Does it break rule number 3? And that's yes, because it's right here. That's a transcendental function. And y's are dependent variable and x is our independent variable. So as clearly you can see. So this is nonlinear. Alright, so here's our next problem. So does it break rule number 1? No, because we're working with this dependent variables, right? And slash derivatives. So let's see. No, it doesn't break rule number 1. Therefore, it doesn't break rule number 2. So now we gotta look at rule number 3. We look over here. We got a function that can contain another function slash transcendental function. And so right here, no, it doesn't. Apparently, it's not. So now we're gonna have to look for rule number 4. So now we're looking at our independent variables and seeing if they're messing anything up. No, the coefficients look like they're doing everything there sufficiently. Therefore, this is linear. So I hope you guys understand how to do this. Which ones are dependent, which ones are independent. Our dependent will be y, and our independent will be x. And so now we rewrite it implicitly. And so if you are pretty good at this, you wouldn't need to. So these steps are just so if you really have a hard time doing this. And so this becomes y prime and cube. And so you could clearly see that this is a nonlinear differential equation because this following term. And so we just say nonlinear and explain what term is not giving us our linear differential equation, and we have our answer. Alright, let's take a look at our next example right here. So the first 2 rules we have to take a look at, it's the power one and the multiplication one. And so now we'd like to take a look at our dependent variables. When that's going to be our y and our differential equations, our derivatives, which are going to be y prime and y double prime. And they don't break the rules, so now we look at rule number 3, which is the transcendental functions. And so we could clearly see we have two transcendental functions slash functions that contain our something else within it. And so right here we have cosine of x and sine of x. But remember that the definition of the transcendental functions says that we have to have our dependent variable contained within it. And so these are contain the independent variable, so that's wrong. So we don't have to worry about those first three rules. So now we take a look at our last rule. And what our last rule is asking us is the coefficients. And so now we take a look at our coefficients. And this is not a coefficient, this is just simply the function, which is going to be f of x. And so that's, we don't have to worry about that. So now we got to take a look over here with cosine of x, which is our function. And we got to take a look over here. Well, we had another transcendental function was e of x. And so we take a look at those, and we determine that by our definition that the x has no boundaries of what it could be for being the coefficient. And so therefore this is a linear differential equation. So you just put linear equation or linear, and then explain, maybe you have to explain why, and you just say it satisfies being the coefficients being in the front to satisfy this, and you explain all the rules if that was the case. Alright, so here's our next problem example, and unlike the other problems we've been working with, which have been ordinary differential equations, this is a partial differential equation. And so now we're going to determine if it's nonlinear or linear. And so our independent variable is going to be u and v. So we got two independent variables in this case because we have partial differential equations, and we have these omega symbol on top. And for certain mathematical constructs and concepts, this symbol is really important. But in this case, we're just going to refer to it as omega. And so right here, we're going to take a look at our problem. So first, what's our dependent? We define what our dependent and independent variable is. So we can't rewrite this implicit because this is a partial differential equation. And so now we need to identify the rules for this. So does it have a power? No, right? Because the power would mean that there would be something on top. Is it multiplied by a differential equation? A partial differential equation? No, it's not. Or by itself? No, it's not. So rule number 3, is it transcendental? No, it doesn't. It doesn't have sign contained within this. And rule number 4 says about the coefficients, and there's no coefficients here. And so this would be a linear partial differential equation, if you want to be more specific. And the last couple problems we did, we could, if you need to be more specific, then you say ordinary or ordinal. Alright, so this is our last problem that we're going to do. And so this is another partial differential equation. And so what are the first two rules is the power one and the multiplication one. And so right here we have two independent variables on the bottom, and they're being multiplied by the top by two dependent variables. And so if two dependent variables are multiplied together, that breaks our rule number 2, and so therefore this is nonlinear. And there's no transcendental function, and there's no coefficient, so, or self-containing function, right? And so this is our answer, nonlinear partial differential equation. And so if you guys want to see more videos like this or more content like this, you have any questions, please leave them down below in the comments. I'm going to be making more videos like this with in terms of differentials and the class. And if you like this video, please give it a thumbs up, subscribe to my channel, it will help a lot. And I make other math videos for other upper division classes for math / lower division math classes. And I can't wait to see you guys next time. Thanks for watching, and goodbye.